Thanks a lot, Matt, for the introduction. So I will provide a more practical take on how to use an R package and try to, I have two purposes with this talk. First, to show you what can be done if you want to do this kind of analysis, but also to maybe even more important to show how very different packages they can be combined so that you can actually do something which is not feasible just using one package. So I really believe there's strength in utilizing some of the other packages that are around, but I'll get back to that. So it's all about data which look essentially like this. So I have what I will refer to as dose response data. There's a scale on the x-axis, which is the dose or the concentration or perhaps something else. And then I have a response, and then there will be a pattern which is essentially an S shape. So that's pretty important that I will be talking about nonlinear trends, and I will be talking about how to deal with that using fully parametric models. So I'll not be talking about linear trends or dose response trends that are linear functions. So that's kind of the unifying feature of what I'll be talking about, just for you to keep in mind. So what is the background kind of for these kind of analysis? Well, they've been around for quite some years. I mean, in 1940s, 50s, they were in small scale, conducted in toxicology, but that was really experiments with maybe 5, 6, 7 observations. So that's hard to believe, but that's how it was at that time. Then during the 60s and 70s, it was somehow more formalized. There was all the work by Finney, his famous book from 71, Probit analysis, sort of wrapped it all up. It still relied essentially at that time on linearization, so you couldn't fit a nonlinear model directly, because at that point in time it was mostly something you did by hand when you fitted the model. So he did a lot of work somehow to illustrate how it could be done in a practical way, but it was essentially approximations. Then in the 80s and 90s, there were a lot of standalone programs happening to appear, and there were also some macros for SAS and Excel, and they could deal with nonlinear regression, maybe only a few models, but they were more flexible in a sense. And then, well, back in 2005, we started working on an R package for fitting dose response models. And I guess ever since it has evolved just like a lot of other packages, so that it's now quite an extensive structure for fitting these kinds of models. Well, I'll try to illustrate that a little bit later. So what is the current infrastructure? Yeah, well, we recently moved more or less all of the development to GitHub because we are multiple collaborators and it's a lot easier to do it that way. There are currently 4 packages that you can see. There's a DSC, which is kind of the engine, which is also available on CRAN, but is nowadays not updated that often. Then there's a data package, only containing the data that's used in the other packages. Then there's a specialized package for mixed dose response modeling, which is a fairly recent one, and then there's even a more recent one that will deal with a specialized case of utilizing dose response analysis, the benchmark dose estimation. And then actually there's an independent development which will still rely on some of the functionality here, which is still on GitHub, and that's a DSC seed germ, which is specifically for very complex germination experiments. Okay, so that's kind of the infrastructure. My first key take-home message. Well, it seems to me it's a general trend that people, they try to utilize that there are other packages around. So there's not, I would not dare implement the plotting function any longer, because I think now there are much better packages that can do that than I would be able to do so. So use specialized packages for specialized tasks. That's sort of the thought behind. And what does it mean for dose response analysis? Well, we can get nicer plots if we use ggplot2. Still, there's some manual work in that. We can get to much more advanced analysis using the metaphor, the MoodComp, and the sandwich packages, and for the mixed effects, we use the NLME. So we really exploit that we have multiple packages around. And I will actually show you that very concrete in this first example. So that's binary dose response data. They are from a publication, and actually what I'll be showing you in a publication 10 years ago, what I'll be showing you here is beyond what they did in this statistics paper from 2009. So there are multiple curves because there were 4 types of selenium that were used in this experiment. There are no replicates per type of selenium, so it's not the greatest of experiments, but at least we have 4 dose response curves, and then we can fit them in this using these few lines. So it's essentially a specification, much like if you know GLM. What is different here is that I specifically indicate which nonlinear S-shaped model I will fit. So I'll fit a log logistic 2-parameter model, but I think essentially the rest could be similar to what you would see in GLM, except for the curve ID, which specifies that we have 4 curves. And you can do that now. I just pulled the package from GitHub because that's the most recent we have. A basic visualization, which is still part of the package, is to show the fitted curves with the data. Traditional graphics, not too fancy. There's something with the break here, which is hard to actually reproduce in ggplot2 at the moment. So that's why we still use this from time to time. You can see fairly nice fits. In this case, you wouldn't really think that there's any issue. Okay, moving on, what is the really important part? You would like to estimate effective concentrations, and you can do that easily using the function ed, which is part of the package DRC, specifying your model fit, which effective concentration you are looking for, and then what kind of confidence interval you would like to have. And in this case, I will use the delta method, and actually because it's ED50, it's the delta method on the identity, but I could here get any EC value, so it need not be 50. And you can see I get the estimates here, and I get the standard error and the 95% confidence intervals. That's fine. What if I want to utilize that we have other packages around, powerful packages? Well, I could use a robust standard errors. It's one single argument that I add to my ED function, and then it will compute it all again, but now with robust standard errors using the sandwich package, which is also from 2006. So I'm using a package that have been around for a long time and which are really great. So we can see there are some changes in the standard error. So it seems like the original model was to some extent misspecified. You can easily see it because the standard errors, they change in some places dramatically. What else can I do? Well, I can move on and then use the package MoodComp on top. So I retain the sandwich argument up here so that I have robust standard errors, but on top I add that I would like output which could use for MoodComp equal true, which means that I can feed my output directly into GLHT, and then I get something like this, which is just the basic output you get when you use GLHT. So I started out with a dose response model, then I applied argument to get robust standard errors, and then I applied another argument, and then I can squeeze it into GLHT from the MoodComp package. I think that's really nice, and you can even put it one step further. You can make pairwise comparisons. And that will then be for any EC value you would be interested in, and you will have it with your robust standard errors if you like. So it flows all the way through using those 2 extra packages. So I think that's really one example of utilizing that there are powerful packages around. The other example that I will have is dealing with more, which are now more common, complex dose response experiments where there are really a lot of curves. How could you address that? Of course, you can fit a joint model. Depending on your type of response, that can be very difficult. Some years ago, there was a paper by Young and Kopp-Snyder, and they showed actually that you can sort of replace, so to speak, your nonlinear mixed effects models by simply fitting curves one by one, and then extracting the relevant information. You combine information from the individual curves in your second step, and then you get something which is very close to what you would get if you could fit the nonlinear mixed effects model. So you can sort of break down the simultaneous joint model into a lot of simpler model fits, and then you just need to combine them end of the day. So I think that's really a powerful extension, which is also now more or less extending widely what you can use dose response analysis for. It requires some more code because I need to fit the separate models, and I think this is not the most elegant way of doing it. I'm using a plier function, so I guess that's already a criticism, but I'll be fitting a 3-parameter log logistic model, but for each of my individual dose response curves, which in this case actually are for time to event data. So there's another complication here that this is not continuous or binary, but it's event time data. I fit all the separate models. I sort of combine them. In the next step, you can see here, that's another function. At the moment, it looks like this, and I hope that we can wrap it up so that it will be just one command that we have in the package in the future. But we're still working because there are very many complex designs around. So this is an operational suggestion for the time being using the plier package. What do we get out of this? So I here fitted all the separate models. That's happening actually here after I've set up the function. So fitting a model for each experiment, each biotype, each depth, each temperature, each pot. So I have really a lot of separate model fits. Then I sort of give them names and add some additional column here. And how does it look? It looks like this. So we can see I have experiment, biotype, depth, temperature, the pot, and then I have my estimated D from the 3-parameter log logistic with a standard error. I have the D, the upper limit, and I have the T50, which is the crucial parameter telling when I had 50% germinating. In this case, it's seeds germinating. And then I can now use the metaphor package and simply exploit. I have the data in the right format, specify my estimate of interest, supplying the standard errors, supplying the model I would like to look at, fit this model, using this package, which is documented in a paper from 2010, so it's also been around for some years. And then I get an output where I could, as the next step, now I will not show you, but just give a hint, I could make pairwise comparisons or model reduction as for any other model. So I could proceed to use MoodComp once more. So I could even combine MoodComp and metaphor here. So again, using that there are other packages around. Then I have another example just to show you maybe something else. It's a very recent addition, so we haven't even written up the paper on how this is working, and that's that dose response analysis that covers in principle also estimation of species sensitivity distributions. And I have a data here, it's published in 2004. You can get it from this package, so I simply use fit this plus to extract the data, and then in this case, what I'm looking for is that I will be fitting a distribution. But what is interesting for me is that people usually show it as an S-shape again. So the analysis will eventually end up that people will show a fitted S-shaped curve, which in this case is the cumulative distribution function. I can specify it in much the same way as I did for the two other models using DRM, the key modeling function in DRC, specifying now there's only something to the right of the tilde because I only have my variables that I want to have fit to a certain distribution. I use the same distribution as in the paper from 2004, a bird type 3 distribution, which is a special case of a generalized log logistic distribution. And then you get an output like this, which looks similar to what you have before. And these parameters are usually not reported because what you are interested in is something like this. And you will see that very often when you look into papers on a species sensitivity distribution, they show the fitted curve. And then, of course, the story is kind of the same, that you would like to estimate for a certain level here, what is the concentration or the value down here. So that's the hazard concentration 10, for instance, that's for 0.1. And where are we here? You can do that easily, again, using the ED function. I get estimates and standard errors. Quick look, the standard errors are very large, so you would not want to use the delta method for the interval, but you can use inverse regression, then you get sensible confidence intervals as well. And I think then I'm more or less done. Concluding remarks, so I think you've seen simultaneous inference because I linked to MoodComp, sandwich, two-step approach using the metaphor package, multiple other types of models and distributions that can be fitted. I've provided a few examples, recent papers where it was used. For the future, exploiting that, perhaps we could even combine metaphor and sandwich. I think that would be very interesting. There's a need for implementing more general parametric event time models, which seem to be very interesting in biology. And then another idea is here, I just tossed it at you more or less, biphasic models for intake of nutrients, which is a rising area where there's not that much modeling taking place at the moment. So if you have any questions or interested in any of what I said, please talk to me or drop me an email. And of course, my slides, they will be available. Thanks a lot.
Excellent timing. So a lot of interesting things to ask about. So who wants to start?
Thank you, very interesting. There are alternative ways to fit dose response curves in a way with some constraints, for example, monotonic, either increasing or decreasing, and then other types. And some of them, I think, were implemented using extension of the MGCV package by a student for Summerwood, and I think it's on CRAN also, that part. I understand the rationale of fitting a curve following a very specific, for example, log curve or something, but have you ever thought about using these more flexible but less constrained, probably, methods for checking, in a way, some of the curves you have, or...
Well, it's a good point that I'm hard driving on the parametric models, and I think essentially this is based on what people want in the applications. So, but of course, it would be interesting to do something where you have a more flexible model checking. Yes, but it's not in demand at the moment. So, but yeah.
Other questions?
So yeah, thank you. So I just had a question about, so you do these, you do fit these models for different responses one by one,
yeah.
But at the beginning you also had this extra argument in the DRM function curve ID. So I wonder what did that? So you when you define that ID like that type, that means the type variable comes as a factor in a linear way into your model, like, so you estimate a type, a specific parameter. So it's different.
Separate parameters per curve ID.
So then it's different than fitting a separate model to each type.
Yeah, it's a good point. In some cases, you can fit separate models and then combine them, or you can fit a joint model. And I have to admit that I nowadays favor more fitting separate models and then combine them than fitting more complex models in one go, because I think it's a lot of trouble, and the benefit are not always that visible.
So if they're separate, then you need to apply this metaphor before doing these comparisons?
Yes, okay. Exactly.
Thank you.
Yes.
Excellent. So I was wondering, before we turn to the next speaker, did you say that you were moving away from CRAN, or?
Yes.
So this means that your package will not be hosted on CRAN anymore?
It will be, but it will not be updated as often as we make changes, because that's very often, and to me it's a lot of work to have it on CRAN every time. So we will maybe update once a year on CRAN, but we will update on GitHub.
It will still be there?
Yeah, it will be around, yeah.
Okay.
Yes.
Excellent, thank you.